Okay, this video is the second one in the forces series and about resolution of forces. And I just thought we'd just go back to mass and acceleration and weight and just have a little bit of a recap of that, and just by way of looking at Galileo. So this isn't particularly to do with resolution, but we'll come to that in a minute. And we'll just go back to Galileo's famous experiment where he dropped two metal balls off the top of the Leaning Tower of Pisa. There must have been, when he did this, all the other scientists must have thought, why didn't we do that before? Because I think everybody had assumed that you've got a heavy ball and a light ball. These are metal balls, very little air resistance. Obviously the heavy one is going to fall to Earth faster. But Galileo proved that that wasn't the case by actually doing it. And as we can see on this right-hand diagram, the Galileo experiment, they're both falling together. And why is that? Well, essentially, it comes back to Newton's second law of motion, which at the time, of course, they haven't been formulated because Newton lived after Galileo, but F equals ma. So if we just rearrange that, we see that the acceleration is equal to the force over the mass. We've said in the previous video that the force on a body in the Earth's gravitational pull is equal to its mass times the times g, it's acceleration due to gravity. So therefore F over m becomes mg over m, the m's cancel, and that's equal to g. So acceleration is g, regardless of the actual mass of the object. So that is basically it. So I just need to bear that in mind. I mean, that's a good illustration, I think, of, that sort of really says clearly the difference between mass and weight. So there we go. So I thought that was just worth doing as an introduction. But now we're going to move on to what this video is mainly about, which is resolution of forces. What does this say? We can split a force into two orthogonal, which means perpendicular, components that define the effective force in each of those two directions. So here we've got a force F acting in this direction, and it makes an angle theta with the horizontal. And therefore, the effective, imagine the sort of the amount of pulling that's going to the right, to the right, this will actually be equal to F times the cosine of theta. And in the vertical direction, well, it's equal to the cosine of this angle here, which is theta minus 90 minus theta. But that is the same as F sine theta. So you could, if this angle, say, was 30, you could actually say this was F cos 60. Personally, I think it's better to actually stick to the convention of cosine and sine. So the cosine, so is this angle, is this here, which makes it an angle theta with the actual force, and this is the sine. It's a question of being consistent, I think, but I think this helps to to sort of clarify just what you're supposed to do when, and I think makes it easier to check. But anyway, so why do we do this? Why do we want to split it into two things? Well, very often we can help us to solve the problems. That's the be all and end all of it, really. Because what's happening in the horizontal direction and what's happening in the vertical direction are essentially, potentially in many ways independent. So this is quite useful, and when we look at some examples of problems, then this will probably come clearer. Kind of the other thing comes out of that is that when we're looking at these two orthogonal directions, what we're effectively doing is building up simultaneous equations, and that's what actually helps us to resolve for unknowns. So we can actually have two unknowns in two directions, and we can use those in order to solve for the two unknowns. Okay, right, if that's not clear, then don't worry about it. We're going to come to that in the examples, and here is one of those examples. Okay, so let's have a look at this. A particle of weight 24 newtons is held in equilibrium by two light inextensible strings. So the conclusion from this is that this is in some, we talk about weight, so weight exists when there is some gravitational pull. You know, it might be on Earth, it might be on the moon. It doesn't actually matter for the purposes of this problem, but it's 24 newtons. One string is horizontal, that's this one, and the other string is inclined at an angle of 30 to the horizontal. So the tension in the horizontal string is Q, and this one is P. So this is an angle of 30 degrees. Find the value of P, find the value of Q. Fairly straightforward question. So I would suggest, you know, we draw our own diagram. We don't try and sort of mess this one up. So I've kind of cheated really, because I've just copied this over here. And in the process of doing that, what have I done? It means I haven't got a proper space to write my mass there, but that would be well, it wouldn't. We don't know what the mass is actually, do we? So that doesn't matter. I've scribbled out where it says newtons, in line with my suggestion that you don't put units on diagrams. And that we're talking about a weight of 24 newtons. So that is the this force here. Okay, so now this what we're doing in this problem is this force P here, we're going to resolve into its two directions, and so very similar to the example above. So this horizontal direction, the effective force is P cos 30 degrees, and in the vertical it's P sine 30. So we've replaced this, for the purpose of our calculations, we've replaced this force here by these two. Now that's nice and easy, because then when we're actually looking in the vertical direction, we can see there are two forces. There's P sine 30 acting upwards, and this 24 acting downwards. They must be equal because the particle is held in equilibrium. So we can say therefore that P sine 30 equals 24, and then sine 30 being a half means that P is 48 newtons, working in newtons. And then similarly, when we look at the horizontal, then Q is going to be equal to P cos 30. Again, there's no motion, no acceleration in the horizontal direction either. So Q equals P cos 30, and we know that P is 48. So, and cos 30 is root 3 over 2. So therefore Q would be 24 root 3 newtons. So that's that one, fairly straightforward application of the resolution of forces. Just going back to the weight issue, yeah, this is 24 newtons. So had this been on Earth, where let's say the gravitational constant G is 10 approximately, then that would have suggested that this mass was actually 2.4 kilograms. If it had been on the moon, where the gravitational constant is, I can't remember, maybe 1, let's say, then it would have corresponded to a mass of 24. So just an indication there. But all that's taken out of it for us because we just told it's 24 newtons. Right, so that's that one. Nice little problem. Let's look at this one. It's not too dissimilar. It's slightly more complicated. Four forces acting at a point. The forces are in equilibrium again. At a point, so they're in actual fact there's no mass in the center, but it sort of doesn't matter really, because you know, if you can imagine, there's just a weightless ring here, and you know, there are strings pulling in each of these directions. If they certain values, these, then the whole thing will be in equilibrium, and that ring would not move. So it doesn't matter that there isn't a mass there. So it says show that P equals 14. So here, first of all, we're going to resolve vertically. So this P is opposing the effect of this and this. So if we resolve this and this force vertically, then what we get is P equals 8√2 cos 45. So that's the effect of this one going vertically down, plus 12 sine 30, which is this one going vertically down. Sine 30, note. This will be cos 30. This one going down is sine 30, 12 sine 30. And so we just kind of work that through, and that gives us 14 newtons. And then resolving horizontally, well, just more or less more of the same really. This Q is going to be equal to 12 cos 30. That's the portion of this acting horizontally, minus, well, this is kind of helping this. So we could start off with this on the same side of the equation as the Q to be perhaps completely rigorous. But I brought it over onto the right hand side, so it's minus 8√2, and again this is cos 45. So we just work that through, and yeah, we've got a couple of surds involved in here, so we're going to get a decimal, so it's 2.39 newtons. If we work that through, that's to 3 significant figures as defined there. So this is basically what we do with with resolving forces. Another thing we can say about forces is we can actually, if we relate this to vectors, we can basically form a triangle of vectors where the lengths correspond to the actual force. So here, just translating our picture slightly. So here we've got F. Horizontally, we've got F cos theta, haven't we? And vertically, we've got F sine theta. Let's say we only knew the horizontal and the vertical, and we wanted to ask ourselves, well, what is the net result of these two forces here? So it's kind of unresolve it, if you like, back to the original force. Well, that would be so that would be the square root, just using Pythagoras, because we're using lengths to represent the value of the forces. So it would be the square root of F sine theta all squared plus F cos theta all squared. We can factorize our F out of that, and then sine squared theta plus cos squared theta equals 1. So we're just left with F. So that's the force F there. Okay, so that's quite useful in some circumstances. So let's have a look at this one. A particle of mass 10 kilograms is subject to a force of 4 newtons horizontally and 3 newtons vertically. So we don't know, it might be a string pulling it or somebody's finger pushing it or whatever. Find its direction of travel as an angle from the horizontal and its acceleration along that direction. Well, here we've got this this same thing that we've got above. So the total force, and see, I've conveniently chosen a Pythagorean triple, whatever it's called. And so this force here is 5 newtons. So, all right, imagine our 3, 4, 5 triangle. 3, 4, and the hypotenuse is 5. So we're using the sort of geometric representation of it. So that is the force. The angle is, well, this angle is, well, the tangent of this angle here, the one we want to know, is 3 divided by 4. So in other words, the angle itself is inverse tan of 3/4, which is 36.9 degrees to 1 decimal place. Incidentally, just at this point, is that whenever you have answers that are approximations, you truncate it to so many decimal places, you always put the accuracy in your answer. And here is 1 decimal place. Okay, so that's the angle. The acceleration we can now work out from the above is the force divided by the mass. The force along this direction is 5 newtons, as we've established here. The mass is 10, that's what it says. So 5 over 10, so it's equal to 0.5 meters per second so that illustrates that one. Right. So the last thing, inclined planes. So you see lots of these problems at A level, and basically what this normally requires us to do is to resolve in 2 directions, but not vertically and horizontally, but along the plane and perpendicular to the plane. Okay, so here we've got a mass of kilograms. So its weight, if you like, vertical weight down here is mg, mass times the gravitational constant, this being in newtons, of course. So if we are to resolve that weight along the plane, we're going to get mg sine 30. There is a component going vertically. I'm not thinking about perpendicular to the plane in this example. Just looking at along the plane, so that's mg sine 30. Now we've also got this force P, which is pushing it back up the plane. Incidentally, we're assuming this is like a smooth plane. There's no friction involved. We haven't done friction yet, but that's in the next video. And so what we want to do is to resolve that P both along the plane and perpendicular to the plane. Now, I've not done the perpendicular similarly, just done the along the plane, and that would be P cos 30. So yeah, so basically, because this is not moving, therefore it's in equilibrium, no acceleration, then we can say that P cos 30 equals mg sine 30. These are the only 2 forces acting on this particle, and it's not moving along the plane. So that's what we've got. So just if we're to just kind of elaborate that, so say that m was 10 kilograms, the mass was 10 kilograms, then we would calculate the force P as being the mass times the gravitational constant 9.8 times tan 30, which is 56.58 newtons to 2 decimal places. So that kind of makes sense, really, because as this angle decreases, if we kind of did the whole thing but at a sort of shallower angle, then theta is going to decrease, and therefore tan of theta is going to get less and less and less and tend towards 0, in which case the force P would tend towards 0. It would have to, otherwise we're pushing it up the plane. So that is about resolution of forces. Those are simple examples. We're going to come to do some more difficult things. but for now, that is it. So I hope you found that useful, and I'll see you in the next video.